Sorry, that video got abruptly stopped because a interruption came. So we continue. So basically, um, for the for the elements of a canonical ensemble, NVT is a constant for its elements. So in other words, I can tell that the macro state for all elements in a canonical ensemble is defined by NVT. So that is a similarity, right? So it's a collection of similar but non-interactive systems. So that is the similarity for a canonical ensemble. NVT for those systems are same. But then you know the concept of macro state and micro state, right? So every micro state is defined by different micro states. So in the case of canonical ensembles, between the micro states, there is a variation in the energy. Basically, this is internal energy, of course, internal energy, and we represent it by EI because it's a varying quantity. So that is the point. So we, in a canonical ensemble, we have all the elements having similarity in terms of their macro state, where their NVT defines its macro state. But if you look deep into each of those elements and compare those elements, they do vary in terms of their internal energy. So that is it. For example, let me draw a figure over here. Normally we represent a canonical ensemble like this. You might have learned this in your BSc, I'm sure. Right. NVEI, NVEI, NVEI. But you will, of course, you will see the books which write NVT, NVT, NVT. But that's another way of representing the same thing because they are just talking about the macro states. They are telling that its macro state is same, NVT. But I'm just representing it in all of these elements in terms of its micro states. So here, in the case of canonical ensemble, in order that so this is a collection of systems, but it is protected from its broad environment. So naturally, I will that is what this red wall is representing. This is representing some kind of a thermal insulation. So I don't allow any in temperature to change from outside, right? And but this wall does allow energy to exchange. How? Because these are all these elements, I construct that they are all placed in a heat bath at a temperature T. So that is my concept. So these elements do exchange the energy through the some kind of a diathermic walls. Okay. So that is the speciality. All those elements do exchange energy through diathermic walls. So what is the speciality here? Now I am in a situation where that is what this concept is talking about. So this is the canonical ensemble. I took it as an ensemble, as an example for it. For example, if I look into the system of a particular macro state in Vt, at that instant of time, the system will have a particular N, particular V, and a particular temperature and a particular energy. And if you look into an instant, say in the T1, I have N, I have number of particles, a particular N, particular V, particular T, and a particular energy. Let me call it as E1. And if I look into some other time, I will have similar. I will notice that there is a particular number of particles N, particular V, particular temperature, and also a particular energy. Similarly, for another time T3, I have N, V, T, E3. So what I notice is that in all the three times, their number of particles, volume, temperature are all constant, but they do vary in terms of its E1, in terms of their energy, like E1, E2, E3. So I can always take a time average system, right? If I can always take a time average system. Okay, at T1 what was it? T2, T3 what was it? So I can take a time average system and represent the statistics of the system. But this time average system was replaced in the ensemble by telling that, okay, you take any time T, I will put there in that time itself all the possible microstates simultaneously. So that is why I tell that it's a static time independent picture. So in that time itself, I have all the possibilities here. For example, NVE1, NVE2, NVE3. I represent this one at the same instant of time. So that is so it's definitely an artificial construct, but for a theoretical building up of the statistical mechanics, this concept really helps us. So that is why Gibbs brought in this concept of ensemble, and the concept of ensembles will be utilized widely in the further discussions of the statistical mechanics. Okay. So there are three kinds of the ensembles, as you know. They are microcanonical, micro canonical ensemble, canonical ensemble, and the grand canonical ensemble, which I will explain in some other video. Okay, thank you.